Hello, my name is Robert, and today I present you our paper with the title S3AD, Semi-Supervised Small Apple Detection in Orchard Environments. Reliable and accurate detection is a crucial aspect for many precision agriculture applications. For example, automated pre-harvest yield estimation, quality control, and fruit picking, just to name a few. However, building such an object detection system has proven to be challenging for most crops and application scenarios. For instance, apple detection in orchard environments is still difficult. Two important reasons for this are the absence of publicly available large-scale datasets and the small apple size, which is often even made worse by occlusion caused by other apples, branches, or leaves. Small objects are difficult to detect due to the downsampling performed in convolutional neural networks and hardware limitations that make processing of high-resolution imagery with state-of-the-art systems often not feasible. In this work, we address the lack of large-scale datasets by approaching the problem from a semi-supervised perspective, which decreases our reliance on labeled data, and by collecting a high-resolution dataset that fits the semi-supervised formulation. To better deal with the object size and occlusion, we utilize attention-based selective tiling, which lets us increase the object resolution in the feature map without needing vast computational resources. The dataset for semi-supervised apple detection was acquired over the course of 1 month in September 2022 in collaboration with a monastery in a small German town. For this reason, it was named Monastery Apple Dataset, MAD. For data collection, we used the drone to record high-resolution video footage of individual trees from multiple perspectives. After the collection process was complete, 105 frames were manually extracted to ensure data diversity and subsequently annotated with bounding boxes. Two examples are shown on the right. In total, the dataset contains 14,667 labeled instances, and from the remaining data, 4,440 unlabeled frames were automatically extracted. To make efficient use of the collected dataset, the semi-supervised small apple detection system, S3AD, was developed. S3AD consists of 4 stages, which we now explore in a bit more detail. The first stage is called tree attention, which implements the idea of search space reduction via context information. This is done with a 3-stage residual U-net that locates the tree crowns by predicting attention maps on a highly downscaled version of the input image. In our case, the longer side is rescaled from 3840 pixels to just 512. In this case, the context information refers to the part-of relationship between the apples and the tree crowns, which means that all objects can be recalled by just looking at the tree crowns. During training, tree attention uses approximations of the tree crowns that are generated by computing the alpha shape of the bounding boxes as ground truth. In the next step, the selective tiling module extracts promising image regions or tiles for further processing by moving a sliding window over the attention map. And if the mean attention value of a given window exceeds a certain threshold, the corresponding image region is selected for further processing. The tiling allows the detector to process the input without initial downsampling, and thus improving the detection of small and occluded objects, even with moderate computational resources. In the following stage, the extracted image tiles are processed by the detection module, which is a faster RCNN with a feature pyramid network that was trained in a semi-supervised fashion with SoftTeacher, which is a pseudo-labeling framework that uses the student-teacher method, in which the teacher learns to generate pseudo-ground truth from unlabeled data, which is used by the student in combination with labeled data during training. In the last stage, False positives are filtered and the per tile results are merged and mapped back onto the original image. Lastly, non-maximum suppression is applied to obtain the final results. Now let's take a look at the results. To evaluate our system, we compared the average precision of our approach on the MET test split with several fully supervised baselines, most of which specifically address the detection of small objects. Additionally, we evaluated the impact of selective tiling has on SAT's performance. And, as shown in the table, selective tiling alone increases SAT's average precision by 1.5%, showing the overall benefit of this method. Comparing a version of SAT that only uses semi-supervision and no tiling with the faster RCN baseline shows that semi-supervised learning by itself significantly improves the performance, since it increases SAT's average precision by 4% compared to the faster RCN baseline. By using semi-supervision as well as selective tiling, the average precision increases by 5.5% compared to the baseline, which represents a significant improvement. When comparing SAT to the more recent path aggregation network and deformable data, who both report good results for small objects in their original publications, SAT still manages to outperform the path aggregation network by 4.5% and deformable data by 3.8%. We also compared our approach with the small object detection systems Sniper and Autofocus, which both use a more powerful ResNet 101 backbone, but nonetheless SAT outperforms both by 3.7 and 0.5% respectively. The qualitative comparison shows that SAT is much better at finding objects that are very small, clustered together, or heavily occluded. In the images, the red arrows indicate missed apples and the green arrows indicate that they were correctly detected. However, since it is too difficult to spot many of the details in these images, let us look at some zoomed-in regions. From this detailed view, it is clearly visible that SAT is much better at detecting very small and heavily occluded apples, which are always missed by the other systems. Lastly, let us take a look at the results of tree attention and selective tiling. Our evaluation shows that the binarized attention maps predicted by tree attention are able to recall 99.71% of all objects in the test split, while, as can be seen in the two examples, significantly reduce the search space. These attention maps enable our selective tiling module to process only 62.47% of all possible tiles, which results in a 24.2% runtime reduction compared to processing all tiles. If we compare the results of SAT with and without tiling qualitatively, the comparison suggests that even though selective tiling does not contribute to the overall performance as much as semi-supervision, that it is still an important system component for the detection of edge cases that are either extremely small or occluded. In summary, in this work, the first semi-supervised apple detection dataset is presented and a novel semi-supervised apple detector is proposed that uses task-specific attention to perform efficient selective tiling and outperforms all fully supervised baselines on the MET dataset. Thank you for your attention. If you like the presentation, you can scan this QR code and check out our paper. Goodbye.